morning and welcome to our introductory session on the Agricultural Conservation Planning Framework. Thanks for joining in, those of you who are members of our remote audience and to folks here at Science Hall. We're being hosted here by the Department of Geography and the Wisconsin Extension Service. So my thanks to those folks for setting this up. We're going to take about an hour and 45 minutes or so here to introduce the ACPF and some of its capabilities. So the Agricultural Conservation Planning Framework there's actually three pieces to it. There's a planning concept, there's a database behind it, and then it's our GIS toolbox as well. I thought I'd actually start by giving you a brief history of the project. It goes back about 4 or 5 years now. We undertook this as part of a conservation innovation grant funded by NRCS, and that grant was awarded to the Environmental Defense Fund in 2011. And our part in that project was to come up with GIS tools to identify appropriate places for conservation practices on the landscape. And as we went through that process, we kind of found just having a list of practices wasn't quite sufficient, that we needed a kind of an underlying concept behind that. And so that's kind of how the ACPF kind of coalesced then into its 3 parts, if you will. We did really, I mean, the availability of the data is what allows the ACPF to work. And the initial database covering it for land use and soils, covering down to the field level, the states of Illinois, Iowa, and southern Minnesota, was undertaken as a separate project beginning in 2011. We published a concept paper on this in the Journal of Soil and Water Conservation in 2013. And then we held our first training workshop in Ames in 2014. We've had 3 training sessions since then in Ames and Mankato, Minnesota. So this is our 5th training session, and we're happy to be able to come over to Wisconsin to introduce folks over here to this project and well, the ACPF as well. We had 2 papers that described the ACPF in detail, the development of some of the tools, and testing and planning scenarios, and evaluation of the riparian assessment framework that we've come up with as part of the ACPF. That was published in mid-2015. So all the papers that have been published on this are freely available, and the links to those papers will be given at the end of my remarks here. We released the ACPF Toolbox version 1 and the user's manual last October. And there's the website. The North Central Region Water Network is hosting the site to make the data and toolbox and user's manual available online. We're grateful to the Natural Resources Conservation Service. They've stepped up since the original Conservation Innovation Grant went through its timeline, and the NRCS is providing additional support now that it's allowing us to expand the database in terms of the area. We're going to be going up into the Red River Valley, covering all the agricultural area of Minnesota, and also being able to go over to the Western Erie Basin at the same time. We're developing new practices with this, and then also developing some training materials so that the 3 of us don't always have to be introducing this to new folks. We'd like to be able to have folks be able to pick this up and undertake some training without scheduling 2 or 3 days out of their schedule to come work with us. What is the ACPF and what does it do? Well, it has a unifying concept. It's kind of underpinned by this concept to for water quality improvement and management, and that's expressed through a conservation pyramid. It's quite a simple concept. I'll be showing you that here in just a couple of slides. It provides, broad base of detailed input data. So it's down to the field scale, but it's at a very broad extent. And so that allows us to conduct analyses, similar analyses down to the field scale across a very broad area. So we can take a uniform approach now across several states for watershed approaches to conservation planning. We've got a ArcGIS toolbox. It looks at a range of conservation practices and identifies locations on the landscape on a watershed basis that are appropriate for those types of practices. And what we're actually trying to do with this is facilitate greater landowner involvement in the planning process, because we're actually providing a full range of options for conservation practice placements down to the farm and field scale. Even though it's a watershed base, you can actually do field scale planning or begin to do field scale planning with the ACPF. And so we're looking at this as a the HUC 12 is our basic unit of analysis, but we have had some users who've taken this up to coarser resolutions and larger basins involved at the same time. So I'll talk about the input data a little bit. When I'm finished here, Dave's going to go into much more detail about this. We've got the soils and land use information, again, available down to the field scale for Illinois, Iowa, southern Minnesota, and eastern Kansas. And we are expanding the area out, and I'll show you that in just a second here. One thing we do not provide is the terrain data, the digital elevation models that the tools rely on, and those need to be acquired by the user, and then that terrain data needs to be hydro-enforced. That allows flow paths to be established then from anywhere in the watershed to the outlet. And that's important to be able to do to be able to evaluate the placement of certain practices and the amount of land area that might contribute water to practices wherever they get placed on the landscape. Okay. And so we've got tools to assist with that hydro enforcement. And so one of the things we'll be doing, and those of you who are here, get ready for a couple of hours looking at this technology for hydro enforcement of the detailed elevation data. Okay, and so our intent with this, in terms of the users, we'd like to have folks who have a modest background in GIS with a couple of days of training and knowledge of a particular watershed to be able to begin with the analysis and contribute to planning through that analysis. We've got a lot of options built into the tools, and this allows the output to be customized depending on the landscape and also landowner preferences. And so the idea is to be able to enable you to take this information out to your watershed community, get feedback about it, and even be able to adjust the output and come up with planning maps perhaps that are consistent in the way that the placement and practice placements develop, but also responsive to landowners and local knowledge. Okay, so here's the area that we're going to, the hatched area there, Illinois, Iowa, southern Minnesota. Those data are available now. That area in eastern Kansas will be online in October. And the other areas are planned for development and release of that input data within the next year or so. This work's being done through an agreement with Iowa State University. They have several students working on this for as many hours as they can spare, as long as their eyes can endure the work of looking at field scale information editing field boundaries and tying everything together to the Huck 12 scale. So if we've got this detailed information available across this wide area, what are, we're going to kind of take you to the concept part of this now. That was the introduction. We have this detailed information available. What are kind of our guiding principles or, kind of underlying, basis for our approach here? And really, there's four ideas that we want to bring forward here. And first, each watershed is unique. I think we all recognize this. There's no two watersheds that are alike. The other piece that's really important is to be able to include landowners and farmers as partners in the planning process. We need to be able to do that. The third piece is that we know that there's not going to be a silver bullet out there. We're going to need a mix of practices. We need practices applied within fields and down below fields, right to the riparian zone, to be able to meet our water quality goals. And then finally, one of the critical pieces is soil management. So encourage all people who work with this to think of themselves, if you're doing watershed management, to consider the soil resource and the importance of maintaining the quality and improving the health of soils. And this can help stabilize the productivity of that soil resource for agriculture into the future. And but it also provides other ecosystem functions. And one, probably the most important of those for watershed management, of course, is the hydrologic function of the soils, water holding capacity, infiltration rates. Soil health is dependent on organic matter and maintaining the organic matter resource. If you've got a healthy soil with active biology, a lot of organic matter in there, you've got high infiltration rates, high water storage, and that means you're going to have less runoff and percolation of water through that root zone. And then that means that water that moves off of a field, there's going to be less of it, it's going to be moving off more slowly. And so those practices, those critical practices that we put in to intercept those flows, they're going to be, easier to manage and maintain because they're not going to be overrun as often. And so thinking about this, we've come up with this idea of the conservation pyramid with the importance of maintaining and improving soil health as the base of the pyramid. So within the ACPF, we don't do any prioritization, spatial prioritization of soil management practices, because we think it's really important for producers to be able to, to be encouraged to maintain and improve their soils no matter where they are in a watershed. But if you think about then the way water moves across the landscape and the sorts of practices that we place out on the landscape to intercept and manage those flows, there are particular landscape settings that are most appropriate for those practices. And so the ACPF toolbox then is focused on those sorts of practices that control water within fields, below fields, and then riparian management as well. And so how do we, so to take this kind of concept then, and I've got this arrow here on the side, looking at that treatment train. So you can think about water quality improvement as, in a watershed, as developing a set of opportunities along each flow path moving through a watershed to intercept and improve water quality. And so the more opportunities you've got to slow water down, filter out sediment and nutrients, the better that end result's going to be at the watershed outlet. And so one of the things we're encouraging here is to think about sequences of practices, stacking of practices, and being able to distribute that stacking of practices to the throughout the watershed to the extent that that's possible. And so then to take this concept and think about developing a toolbox is we've developed this framework then, and it's kind of an organizing way of looking at the different tools that are part of the ACPF. And so you see this color sequence here. If you just flip that upside down, you can see the base of the pyramid up at the top there. No spatial prioritization, as I mentioned. But then if you think about other types of practices that intercept and control water flows, there's particular opportunities to do that in the watershed. And the toolbox then is very much aimed at those other practices that control water in fields, below fields, and then down into the riparian zone. So practices are placed at one of these three scales. That's kind of the concept we've got here. Conservation practices are also designed to intercept particular flow paths. And in the Midwest, we're usually talking about surface runoff and tile drainage. And so this forms this 3x2 matrix. And the practices that we cite within the ACPF can be kind of dropped into any of these kind of cells within this 3x2 matrix. And so the idea here is to think about practices that control tile drainage. And here's several of them listed here. What sorts of landscape attributes do we need to, how do we qualify sites to cite these different practices? Okay, for tile drainage, and then for runoff, there's a few of those types of practices. What landscape attributes do we need to be able to cite those? How do we identify those and consistently through a GIS system? And then also thinking about riparian functions. So when we look at riparian management in the ACPF, we're really considering three ways that contaminants get into a stream. One's by bank erosion, and you've also got overland flows carrying sediment and phosphorus, and then subsurface flows. And generally, you're looking at nitrates there. And so what types of vegetation do you need? How wide a riparian zone do you need to manage those? But then also, if you look at a specific length of stream in the riparian zone and the riparian zones, what are the attributes that you can look at in terms of slopes and elevations above that channel that help you identify what those opportunities might be to intercept those flows? And so that's one of the things that we'll be working through with you folks here in the room, and we'll be getting to this tomorrow afternoon, actually. Okay. And so I'm going to take you through an example application here. This is a watershed that we're very familiar with, the South Fork of the Iowa River in north central Iowa. We've been working this watershed about 15 years now. Just a representation here of the input data. It's recent glacial terrain, a lot of potholes, but the terminal moraine of the Des Moines lobe actually cuts through the watershed down through here, and so you've got these well-developed stream networks at the lower end of the watershed, but a kind of a glacial plain with a lot of internally drained potholes and ditch systems up in the upper part of the watershed. You see the representation of the fields there. It's an intensively farmed watershed. There's a lot of livestock production there as well. And then just the soils information. And this essentially originally was a marsh complex, if you will. A lot of really wet materials or wet landscapes, very hard to cross when it was originally settled back around the 1840s and 50s. Okay, and so I'm going to step through this matrix then and show you a couple of examples of the practices that we cite with the ACPF and how they're kind of distributed here on this landscape. And so that's about a 200,000 acre watershed. It's 8 Huck 12s in total. So it also gives you an example of how you can kind of do this analysis in a bulked way, combining several watersheds together. The tools are very stable. and seem to work for, for, for a variety of watershed sizes. Just depends on how long you're willing to wait for the tools to complete. All right. So, okay. And so, the first cell that we're going to look at here is practices that can that help control tile drainage at the field scale. And two of them here, controlled drainage. This essentially is water table management. You need a very flat landscape to be able to implement this particular practice. And then also with all the depressions we've got on this landscape, a lot of these areas just stay really wet in the spring. They're difficult to farm. What are the alternatives, beyond those orange risers that just take that runoff and put it right into the tile drainage system? There's a variety of different practices you can put in there. Blind inlets are one. You can put in grass buffers or even wetland conversions. And so we've got ways of mapping these out and prioritizing the placement of those practices among a whole cadre of these depressional sites, if you will, that you can find in watersheds like this. Okay, and so just some examples here, looking at these depressions. So this is the uppermost Huck 12 in the South Fork. There's a lot of depressions here, and we've classified these according to depth of that depression, and we also map out the overland flow areas that map, that contribute overland flow into these depressions. And so in this particular Huck 12, more than 80% of the land area, the runoff from that area would flow into a depression before it flow into the stream. So if you were to fully buffer the stream coming through this watershed, you'd only be filtering about 20% of the runoff, according to this analysis. And so being able to map these out in terms of, what are the largest depressions and those that collect the most runoff, so those would be prioritized probably for these sort of treatments in this landscape. Okay. And then drainage water management. So this is the installation of a gate in a pattern tile drainage system at the edge of the field. It controls the water table elevation across the field. You need a very flat landscape. And so what we do with this is allow you to pick a contour interval between, I believe it's 30 centimeters and about 1.2 meters. This is a whole family of practices, the very flattest landscapes. You might be able to put in a single gate to control the water table elevation throughout that field. But as you increase, the variability of those elevations, you might need multiple gates, and the engineering of these becomes a bit more complicated. And so here's a map showing the flattest fields in this watershed. These fields, 40% of the field at least is within a 1 meter contour interval. So you could, be able to control that water table elevation with two gates across at least 40% of each of these fields. So this does not actually reduce nitrate. What it does is reduce drainage volumes, and so the loads that come off of nitrate are reduced by reducing the flow volumes on a seasonal basis. Okay, then looking at surface runoff. Okay, and one of the things we do with this is help the user prioritize those fields in a watershed that are most prone to deliver runoff directly to the stream. And we do that. It's a simple two-way classification, mapping out the proximity to the stream and the slope steepness of each field. And so those fields that are closest to the stream and steepest would be prioritized for runoff control practices. It doesn't mean to say that other fields that are also steep shouldn't have those practices installed. It's just a way of looking at it from the standpoint of which fields should be treated with these practices to observe a response at the watershed outlet. Okay. And so here's an example of of the output for the South Fork. I mentioned that the steepest and most divided part of the landscape is in the lower section with the terminal moraine coming right through here. So we've got most of the steeper fields in this watershed are in the lower part. Okay. And it's obviously picking up the fields that are closest to that stream network. And then a couple of those practices that we might place on this landscape, maybe focusing on those particular fields that are steep and near the stream, would be contour filter strips and then grass waterways. So we have tools for each of those. And so here's a placement of grass waterways among those fields, and then contour filter strips. This is based on, this tool will actually vary the distance between the contour strips based on the slope steepness, following NRCS technical guidance on that. I'm going to shift down now then to look at practices placed at field edges and below fields. And there's several practices that we have out there that are installed using impoundments. And the first one I've got is for water and sediment control basins. And essentially this is a terrace built across a waterway. There'd be an inlet on the upper side of it, and it's essentially a runoff detention basin for temporary storage of runoff. And so you can see we can place several of these along waterways in different parts of this watershed. And again, focusing here on those steeper fields closest to the stream. Nutrient wetlands, nutrient reduction wetlands are another practice that depend on impoundments. This is at a larger scale, so we're usually moving down into areas that have several hundred acres of drainage. And so we move up along drainage ways and test them. It's a very low impoundment, if you will. Okay? And what we want to be able to do is establish a wetland pool here. It's about 1 to 2% of that drainage area that contributes tile drainage into the system, but does not interfere with tile drainage coming from these areas up here. And so here's, this is a CREP wetland. The criteria we use to cite these are based on the Iowa Conservation Reserve Enhancement Program. We don't follow them exactly, those criteria exactly, but we, kind of open up the range of settings where we might put these beyond what the CREP program has. But that's kind of the concept behind it. Okay, and so here's the idea here. Put in the impoundment in the lower part of the watershed. It doesn't interfere with drainage systems in the upper part of the watershed. And so you can get, depending on the area of this wetland relative to the contributing area, you can get 40 to up to 80% nitrate removal, depending on the load coming through there. Varies from year to year. And then looking at the South Fork, the Iowa River, then these are the areas that could be serviced using a nutrient removal wetland that meets those criteria. See, probably a little bit more than a third of this watershed could be serviced with nutrient reduction wetlands. Okay, and then we move down to the riparian zone. Okay, the riparian assessment we have, in order to look at opportunities to intercept different sources of contaminants entering the stream, we again do a two-way classification, looking at how wide, well, first of all, how much runoff, or what the area of runoff delivery is into a particular riparian zone, and then we map out the low-lying area, that area that's within 1.5 meters or 5 feet elevation of the channel. And so those are areas that would have a high water table that you could actually moderate that with a with the roots of vegetation. And so that's an opportunity then to reduce nitrate along through those, if that's wide enough. And so to run this classification, okay, so here's a watershed in Illinois, Lime Creek. The blue shows the streams. The black lines show the runoff flow pathways. The longer these pathways, the longer the longer the pathway, the greater the area of runoff contribution. And then we map out those low-lying areas adjacent to the stream, and we so we can look at how wide those zones are. We then discretize that stream network using a set of riparian assessment polygons, we call them. And then we run that two-way classification with the low-lying area versus amount of contributing area coming in. And then these classifications then convert to suggested widths of riparian vegetation and general types of vegetation that might best be suited to reduce the nutrients coming along that dominant opportunity for intersection. Okay, and so the results for this South Fork are shown here. You see these essentially critical zones that have a wide zone with a shallow water table, a lot of runoff coming in there, very sensitive area in terms of nutrient management and riparian management in the watershed. Probably very among the more difficult areas to farm in this watershed. Suggested these are the areas that should have the widest riparian buffers. Other areas that have short flow paths coming in, don't have a wide zone of low-lying area. You may only need a 20 or 30-foot buffer there to help stabilize the stream bank. And you can see that a lot of this watershed has these kind of tan and yellow colors that would indicate, that you wouldn't usually need a wide buffer in some of these areas. Okay, and so that kind of runs through what we've got right now. We're still working on some things, and we are going to release a second version, and we've got a couple of new tools, and the folks in the training here are going to see our new saturated buffer tool. So I'm going to give you a little bit of information on that. We're also looking to add a tool that cites or identifies potential sites for denitrifying bioreactors. Again, that's a tile drainage edge of field practice. And then we've got a to-do list with a couple of other practices that we're hoping to get to in the next year or so. Okay. And so what's the saturated buffer? Okay, a tile drain takes water, subsurface water from this field, allowing a freely drained root zone for these crops out here, and takes that water right to the ditch or stream. The opportunity to improve water quality by having that water move through this riparian buffer is lost. And so this practice actually reconnects that tile drainage with those riparian processes. It's done with a gate structure that you put a distance from the stream and a distribution pipe. High flows are still allowed to come through and go into the stream, but we found that in the work that's been done, Dan James in our lab has been monitoring these. There's actually there's a number of these in Illinois and Indiana and Minnesota, and the research is ongoing on this, but it's an inexpensive practice that seems very effective. So it's something that we thought we should put out there because of the importance of nitrate reduction in this region. Okay, and so you distribute this water then across that riparian zone and allow that to move through there. Okay, so what the tool we've got is asks basically three questions. Do we have soil conditions in this riparian zone that are conducive to the enhancement of denitrification? And can we avoid unintended consequences from installing this practice? in in a particular location. And the two types of unintended consequences are bank collapse. You know, if you increase the, bring the water table up, you can saturate that bank and have that collapse into the stream. That's not a good thing. And then also the risk of inundating this crop. And so in this tool, we map out areas in a way that helps you avoid those situations. And they'll just show you how this practice, here's a shot of this practice being installed along an Iowa stream. And then the sequence we go through, we essentially use the same riparian assessment framework that we do for the riparian buffers. Look at soils criteria, bank height criteria, and then slope steepness to help identify places most conducive to that. And I'll keep I won't go into details on that right now, but folks here in the room will be seeing a lot more on this tomorrow afternoon. And so this particular watershed looks like it's got quite a few sites that might be considered for this practice. The thing is, a lot of tile drainage in this watershed, and so we'd like to see some of these go in up there. Okay, and so then we come then, kind of full circle on this. We've gone through and mapped all these practices, but I want you to kind of recognize we've just kind of gone through an analysis process. We haven't done any watershed planning at this point. We haven't made any recommendations. We don't have any recommendations. We just know, there's a large number of sites out there that are appropriate for a wide range of conservation practices. Where the selections about where these practices should actually be installed, where money should actually be spent, that's up to the landowners and the folks who work with the landowners in a planning context, who understand the particular, that particular watershed, and work with those producers, to be able to meet their needs as for agricultural production as we move towards water quality improvement. So really, we're looking here then at the application of this, use of this in the planning process. So really, what we're developing then is a menu of options. So this is all the stuff I've just shown you placed on top of each other. It's a really messy map. But if you were to break that out field by field, farm by farm, and show that to individual producers, you'd be showing them a whole bunch of different things they might be able to do in their farm. And then they'd be able to select what's most appropriate for their operation. And that's really kind of the intent of this, is to look at it as a menu. Same, just as you would in a restaurant. You don't go into a restaurant and want to sample everything on the menu. Okay? If you put all these practices, you'd overeat. If you put all these practices on the landscape, you'd be spending far more money than you would need to meet those water quality goals. And well along that track, those funds should probably go to another watershed to meet those goals as well. Okay, so then to use these in watershed planning, okay, and one of the things is I was asked is, well, how are people using this out there? And we don't have a prescription to be able to apply this information once it's developed. We are aware of that folks are using this in different ways, and that's fine. And here's just a few examples where folks have gone out directly and engaged with stakeholders, used the results to identify planning scenarios using the SWOT model. Some folks have taken the output and successfully applied for EPA 319 grants. The Housing and Urban Development provided a $94 million grant to Iowa, and the Army Corps of Engineers is involved with that. It's looking at flood prevention, and the idea here is, rather than building flood walls along our cities, that maybe we should be looking at opportunities to store water up on the landscape. So the Army Corps is using a couple of these tools to map some of these opportunities out and look at the role it might be able to play at the larger basin scale. It's being used as part of the implementation of the Iowa Nutrient Reduction Strategy. We've got a series in Iowa. We've got a series of water quality initiative watersheds. There's 40 of them involved, and the state is contracting with Iowa State's GIS facility to map out sites for saturated buffers and nutrient reduction wetlands, and then we'll be providing this information to watershed planners who have been hired to work with producers in those areas. And then we've also bumped into someone we provided maps to early on in this process, and they were just paper maps. And we went out there like a year and a half later. We weren't sure, what was going on there or anything. But this NRCS DC will still have those paper maps and is using them to work with producers, and we're kind of excited about that. He's using that to cite different sorts of runoff control practices. Okay. So we've got a full menu of conservation practice opportunities. How do we combine them? So I'm going to take you through an example. And so I'm going to show you 2 watersheds. And if you want to, I'm going to try and step through this fairly quickly. This is actually described in detail in our JEQ paper that I'll give you the link to here at the end. And so we've got Beaver Creek in northern Iowa and Lime Creek over there in Illinois. And both of these are fairly heavily tile drained watersheds, but they're different types of landscapes. The Beaver Creek over here is more dissected, whereas Lime Creek, there's a dissected area up in the top of the watershed, but essentially it's a very flat glacial plain out here in the lower part of the watershed. And let's see, so one of the practices that I'm going to take you back to kind of the base of the pyramid here, soil and improvement. And so one of the things we think is important to consider in planning is practices like cover crops that will help improve the soils. And so when we did this analysis, we looked at several different levels of cover crop implementation. None of the fields, a third of the fields, 2/3 of the fields, and all of the fields. Okay, and these maps are not working out for some reason. Drainage water management is another one. There is an area very flat, about 50 fields down here that are appropriate, very flat and appropriate for water table control. And saturated buffers, about 25 to 30 fields that are appropriate for that. It's a good thing I have these numbers in mind, right? Because you guys can't see a darn thing here. And so, yeah, a few saturated buffers are included in some of these scenarios, and then nutrient reduction wetlands that can intercept. We picked the lowest wetland along each tributary stream, and you can see that we've got maybe about a quarter of the watershed that can be served by these in each of these watersheds. Okay, and then so what sort of combinations of practices might you use to meet a particular reduction goal? You can come up with different combinations, but how do you actually assess it? And so what I'm going to take you through a way of thinking about this, maybe that doesn't necessarily involve the use of outside information models, and just kind of look at the information in a little bit of a different way. And I'll start that essentially by asking, well, which of these practices are most effective? Does anyone know? Well, the answer is it depends, right? And so one of the things that we've been involved with the Iowa Nutrient Reduction Strategy, and they did a review of a variety of different conservation practices and looked at the nutrient reductions that occurred. And a lot of these practices are quite effective. What's the problem, though, is this number in parentheses, standard deviations of those effectives, very large deviations, so when I look at this, it tells me that you can't really predict which practices can be more effective than another in a given situation. So in assessing different combinations of practices, why not just assume that all the practices would have the same effectiveness? practices. You don't know what that might be, but you know what your goal is. And so if you've got a specific distribution of practices, maybe you can just identify what that nutrient reduction you need among those practices as distributed to be able to meet that goal at the outlet. Okay? And so think about, a field with two practices. You've got a practice in the field and a practice below the field. If you've got a 50% nutrient reduction for both practices, how much is going to come out at the end, at the bottom? You can actually ask the question. Two practices, each 50%. 25%. You did that by multiplying 0.5 by 0.5. Okay? And so this approach does exactly that same thing. But it doesn't assign a number to it. It seeks a number that gives you an end result. Okay? So if you need a 40% reduction among those two practices, you can do that and run through that process and find that you need about a 26% reduction in both those practices to get a 40% reduction at the outlet. Okay? And so what we do then is calculate the average efficiency needed. We set up a spreadsheet. Each row represents a field, and then columns represent the size of the field and the presence or absence of a particular practice either within that field or below it along the flow paths that come from that field. Okay? And then you can multiply out. So if you've got a bunch of fields that have practices within them and then two practices down below, you're going to need a lot less nutrient reduction averaged among those than if you've only got one practice for each field. Okay? And you calculate that out, average nutrient removal efficiency required among the practices for a whole set of different scenarios developed from those two watersheds I just showed you. Then you plot that against land taken out of production. You could use another sort of economic indicator on that y-axis, but we thought that just mapping this out as land taken out of production gives you a good idea what the long-term costs would be from doing that. And so just to give you an idea here, the top of the scale is around 7 or 8% of the total cropland area in the watershed. And we do have combinations of practices down here that only take 2 or 3% of the watershed out of production, but have nutrient removal efficiencies that are within the range that we see in our practices. And so each of these, and here's just one example of a scenario then that plots down in this lower area. So it's worth trying. We don't know we're going to meet that goal, but we know that if we can expect those practices to function, if they do function as the literature says they might, that we have a good chance of meeting that goal. It's a reasonable start. Okay. And so folks that are here and out online there that are thinking about watershed management, how to approach this problem, they really face a dilemma. They don't have any money, or don't have enough money anyway. They don't have any authority. They can't force a solution, which I think is a good thing. It's not necessarily a problem, but it's part of the dilemma they face. And they're not quite sure of how to move forward. What's the best approach that we should take? And so I'm going to suggest that these sorts of tools can actually help, and we can help spend our money more effectively, maybe. Okay? We can provide choices to landowners, get them involved with the planning process, and just understanding what that full range of options is. It lets you know if you take a certain path. It lets you know what those paths are that you didn't take. And sometimes you don't even know that. Take a particular path. The other thing, if you think about this last one, in 10 years from now, we need to be working on this last point right here. Okay? And while I've seen a lot of use of the ACPF for watershed planning, I think there's a lot of opportunities to answer research questions as well. We do have a few grad students and faculty out of state who are starting to look at some of these issues. But here's just a sample of the kinds of questions that you might be able to, the ACPF might be able to help you address. And so if you've got, edge of field monitoring, how effective is a given practice in a given situation? You can get a number, but can you tell how many other fields would respond similarly? Well, with a tool like the ACPF, you could actually map that out. And then just look at the full suite of practices that are out there. If you take a particular practice, and move from one landform region to the next, what's the distribution or the number of opportunities you see for the installation of that practice, and how does that vary according to landform region? But if you knew that, you might be able to budget for conservation expenditures a little bit more effectively. Okay. Stacked practices. I think this is one of the things that we're really ignoring, and one of the opportunities that we've got out there to improve the information we've got, to identify how conservation practices can work in concert together to give you a water quality improvement. That multiplication factor is probably wrong, right? We just don't know what's right, so we just pick something there. If you look at watershed models, they've gone through those same studies and taken a coefficient and stuck it in the model, right? And so it's not necessarily an improvement. If you could set up studies looking at stat practices, you would be able to do that knowing how many other opportunities, similar opportunities you got in the watershed. And then social engagement. How do you actually go out and take this information to producers? What works best to get them involved? I think all those things are research questions that we could help address. And so I think I'm pretty close to on time here. So I've down to the last couple of slides. Just a few summary points there. We're looking at tile drainage and runoff pathways. Soil health is very important. We stress that at the concept level and encourage folks to think about that in a primary way. Different types of practices are cited. We've got well-known practices that are out there, but if there's other alternative practices that are out there that are still being looked at, you can come up with spatial criteria to help cite those practices. Those can be included in the toolbox. The data are becoming more widely available, and Dave's going to talk about that a little bit. But really, the most important thing to remember is we're just making suggestions with this tool. There's no recommendations that are given. It's not actually a plan. We're developing a planning resource. And if you're actually going to engage in real planning, you've got to go out there and work with your landowners. Okay, and so a few acknowledgments here. Eileen McClellan was the person who led the original Conservation Innovation Grant on this. Kathy Boomer was instrumental in some of the riparian assessment tools, mapping out those low-lying areas. She's developed some code for that. Thanks also to NRCS for their support. Rafael Guerrero and Wayne Daniels, who's here. We've been working with them with the expansion of this and the continuation. And so that support is vital to be able to offer courses like we're starting here today. And then also thanks to Rebecca Power, North Central Region Water Network for hosting the tools online. At the bottom there, I've got some links. The first three are for the papers, and then the last one there is the link for the tools and the data. The question is, will the Wisconsin input data be included soon? And that data is under development, but Dave will talk about that a little bit more. It will be included in the downloadable data next year. I think the folks who have interest in working in particular watersheds, we can provide that information probably within the next few months. But I'll defer to for more detail on that to Dave's presentation. Well, why is Iowa only running 2 practices? Those are the practices they're most interested in. They will be able to run once the setup is done and the data are available, the other practices can be run very quickly. these are the ones that they're really focused on for nitrate reduction right now. That was a decision made by the State Department of Agriculture, and I was not privy to that. I did not make that decision.
What is the process of adding geographies, such as for the rest of Wisconsin, Michigan, Indiana, and Ohio?
Dave will tell you more about that as we move through. He's got specific slides that show the process.
It seems to be dominated by dealing with drained soils and nitrates. Has it been used in a steeper landscape without tile drainage? And does it deal with phosphorus and sediment?
Yes, it can, but bear in mind that this has only been available for a year, and so the use of this to address erosion, sedimentation issues is still in the early going, and we're looking for examples where folks out there might give us experience and feedback on how to make these tools more appropriate for those settings.
How does the ACPF compare to Wisconsin DNR's eval?
We've looked at that briefly, and we've had brief discussions on that. There are some similarities. There are a couple areas where eval goes into a little bit more detail, but I think one of the discussions we might have is, converging these a little bit more, at least for Wisconsin.
The last question, where are the ACPF tools available? And that's on the North Central Region Water Network.
Right, yeah.
Website.
That's that last link on that last slide.